As written on the screen, uh, we are going to start an introduction to thermophysics, of which in this particular class, I'm going to focus mainly on heat, temperature, and thermal expansion. So thermophysics is one of the very important components of physics, such that it is also applying in almost our day-to-day lives because we're going to find out that it is used mostly in engineering, the types of materials that people use in engineering, in construction of bridges, in construction of railway lines. Some of you might even wonder why they leave some spaces or gaps in between the steel or the metal that they use to construct railway lines. It's because they follow the principles of thermophysics. There's quite a vast number of thermophysics principles, things such as even cooling. When you are cooking, you are using heat to the food. It's transferring from the stove into the pot through the liquid that is in the pot until you are done cooking. All of that. So it means in our day-to-day life, just making tea, we're using principles of thermophysics, and we're just going to uh, using this topic or using this class understand the theoretical basis or the theory the theory base, the theory component of what this topic is actually um, about. So the first thing I'm going to talk about is the first thing that you are seeing on the board, which is heat itself. I'm sure we've already heard about what we call thermal energy, and everything that we'll be discussing here will be in relation with thermal energy. So what is heat? This will start as a question. What is heat? So when we say heat, this is just actually the transfer, the transfer of energy. Energy transfer across or along a concentration gradient. So what do I mean when I say the transfer of energy from or along a concentration gradient? Remember, I've always told you, I've already said to say here we are dealing with thermal energy. And when we want to define what heat is, I'm sure we use this term as heat in our day-to-day life. But what exactly is heat? We are relating this term to thermal energy. So thermal energy is being transferred along a concentration gradient. And what do I mean? That means we are transferring thermal energy from an area of high concentration, which means from a surface which has high thermal energy concentration or high temperature in general, because temperature, on the other hand, is the one that is going to tell us the average thermal energy that a material is having. So we are transferring this thermal energy from an area of high temperature to an area of low temperature, and that is what we are calling heat. So it is going to be described as energy transfer. And remember, they ask like they like asking such questions to say what is heat. So what are the keywords you're supposed to know? It's the transfer of thermal energy. And how is this thermal energy actually getting transferred? You're transferring thermal energy from an area of high concentration of the thermal energy, which is an area of high temperature, to an area of low temperature. And just like that, ladies and gentlemen, you will have defined what we call heat. Now, heat is measured in what we call its SI units. And what are the SI units of heat? Some of you might already be familiar with these guys. The SI unit for heat, we call them joules. So heat is represented by the letter Q as heat energy, and it is measured in its SI units. of joules or calories, or calories. And we can convert between these two units of measurement of heat such that they have a certain relationship. To say 1 calorie is equal to 4.184 joules. So these are the units of measurement that we use when we want to describe the transfer of thermal energy from an area of high temperature to a low of, to an area of low temperature. We're going to measure this guy known as heat um, with these units, which is the calorie and the joules, of which you can convert between these two guys using the conversion rate that I've put here down. Say 1 calorie is actually equal to 4.184 joules, like that. So one thing we have to know is that yes, we've described heat as the transfer of thermal energy, and that means at the initial um, of this scenario, or at the start of this scenario, we're supposed to have areas of different temperatures. We're supposed to have an area of high temperature. So I'll say an area of high temperature where heat is going to be flowing from to an area of low temperature, like that, where heat is going to be flowing to. So heat will be constantly moving from that point to another. Thermal energy is getting transferred. So you have to know that as thermal energy is getting transferred from that area of high temperature to that area of low temperature, this guy, the area that is having low temperature, will also start gaining an increase in thermal energy. The thermal energy that is in this area that is cooler, the cold area in this case, is also going to start increasing in such a manner that as this one is reducing, thermal energy is being transferred from this guy to that point. As this one is reducing on this other end, what will be happening to the area that is cooler? It is going to be gaining heat. It is going to be gaining thermal energy, thereby raising the temperature because it is being transferred like that. For example, when let's say you've made a cup of tea, and what do? You get that cup of tea and put it on a table. You've put that system, or you are integrating two systems. You are integrating the cup of tea, which is another system with a hotter temperature or with a higher temperature, with the atmosphere or the room temperature of the room, which is another system with a lower amount of thermal energy. It is cooler in the room. And what are you going to notice? The thermal energy in that tea, the cup of tea of yours, will start getting transferred. There will be an exchange of thermal energy between the cup and the room, the atmosphere, such that at the end of the day, you're going to find that the temperature in the cup of tea is going to reduce, whilst the other system surrounding the cup of tea is going to be gaining thermal energy, and its temperature is going to rise. And this is going to continue until the temperatures of the two systems are actually the same. When it reaches that point, we say it has reached what we call thermal equilibrium. Let me write this term down here. The exchange is going to continue until we reach what we call thermal equilibrium. Thermal equilibrium like this. And what is happening at thermal equilibrium? That means there is no actual transfer of thermal energy in either of the directions. Why? It's because the thermal energy or the temperatures between the two systems that you've integrated has already exchanged its thermal energy such that they've reached at the same level. At the same level. And if you try to find the net movement of the thermal energy, you're going to find that it is equal to zero. Why? It's because the temperatures are the same. And when it reaches that point, we're going to say we've reached what we call thermal equilibrium. And at thermal equilibrium, that means the molecules from the two systems that you're talking about have actually gotten or are sharing the equal amount of kinetic energy of its molecules. Hence, there is no net transfer of uh, uh, of your heat energy or your thermal energy in this case, since we've described heat as the transfer of thermal energy. There will be no net transfer of thermal energy. Hence, we've reached what we call thermal equilibrium. But if you talk about, or if you look at one system individually, you're going to find that it is also going to contain its own energy or its own type of energy that we call internal energy. Internal energy. So this guy is represented by the letter U in physics. And how can we describe what we call internal energy? So this is just the sum of all the kinetic and the potential energies that are in a particular system. It might be a substance, it might be uh, whatever you can talk about. So long as that is an existing material, it is going to have some sort of energy inside it. So this is a characteristic of each and every material that we call internal energy. And this is just going, or in words, we can just describe it as the sum of all the molecular kinetic and potential energies in a substance, of which the kinetic energies is going to be the or due to the motion of the particles inside that that substance, whilst the potential energy will actually be due to the intermolecular forces that are between the subparticles or the particles within that substance. So we can just take this as a characteristic of each and every material, such that each material is going to have internal energy, just like that. And you can actually temper with this internal energy. You can increase or decrease internal energy. You can either increase or decrease internal energy. And what do you think can either increase or decrease this internal energy? So one of the things is if you supply a system with heat, when you supply a system with heat, it is going to do what? When you increase the temperature of the system, you're going to find that this increase in temperature is going to cause an increase in the kinetic energy of the particles that are in that system. It might be a gas, it might be a liquid, it might be a solid, but what you should know is that if you increase the temperature, I'm sure this is not something new. If you increase the temperature of any system, the kinetic energy, the motion of the particles that are in that system are actually going to increase. And if you look at this trade in internal energy is equal to that, these are directly proportional to the internal energy. So any increase in the kinetic energy is going to cause what? Is going to cause an increase in the internal energy of a system. What else? When you do work on a system, when you do work on a system, you're also going to find that you're going to increase the internal energy of that system. For example, if you're compressing a gas, you are doing work on that system such that you're going to increase the uh, the the internal energy of that system. For example, even when you are stirring tea, let's say you've made tea and you start mechanically stirring that tea, you are doing work on that tea, and that steering that you are doing, you're going to find that instead of it decreasing the temperature, it is going to increase the temperature. Why? It's because you are doing mechanical work on that system such that you are increasing its internal energy, thereby directly affecting the kinetic energy of that system. I hope that is clear. I hope that is clear. Okay, so moving on to that, we're also going to talk about another thing just down here. And the next thing we're going to talk about is that this amount of heat that is in a substance, which we've defined as temperature, can actually be measured. The amount of heat or the amount of thermal energy that is in a substance can actually be measured. So in simpler terms, I'm trying to say temperature can actually be measured. And how do we measure temperature? We can use different materials to measure the average thermal energy in particles. And the measurement of this average thermal energy in a particle is used with an SI unit of Kelvin. So the SI unit of the measured thermal energy in a particle is measured in Kelvin, but there are three different temperature scales that we can use to measure temperature. There's what we call the Kelvin itself. There's what we call the Celsius, like this, and there's also what we call, oh, this is Celsius, not Celsius, like this. There's what we call Celsius, and there's also what we call the Fahrenheit. Fahrenheit. Okay, so the measurement of temperature can actually be acquired using these three units of measurement, and we call these the temperature scales. So we have three temperature scales. We have what we call Celsius, Kelvin, and also the Fahrenheit. And we can actually convert between these guys. We can convert from Celsius or from Kelvin to Celsius, from Celsius to Fahrenheit. We can convert to Fahrenheit to Celsius, and from Celsius to Kelvin, and we can also convert directly from Kelvin to Fahrenheit, or still we can also convert directly from Fahrenheit uh, to Kelvin, like that. Kelvin to Fahrenheit and also Fahrenheit to Kelvin. And how do we actually do that? There are formulas that we're supposed to know that can help us master how we can calculate or how we can convert between one temperature scale to another. For example, let's start with the degree Celsius to Kelvin. So I'll write all of them on a single board so that those who are taking notes can actually can do so. So there is degree Celsius to Kelvin. What do we do? We're just going to get your temperature in degrees Celsius, and then you're going to add a constant, which is 273.15, and that is going to give you temperature in Kelvin. You're going to get your temperature in degrees Celsius and add a constant, which is 273 Kelvin. Then the opposite, if you want to convert from Kelvin to degrees Celsius, what are you going to do? You're going to get your temperature in Kelvin and you're going to subtract 273.15, which is a constant like this. So that is how you can convert vice versa from Celsius or degree Celsius to Kelvin and Kelvin to degree Celsius. Then from converting from degree Fahrenheit to Celsius or to degree Celsius, do this. What are you going to do? You're going to get your temperature in degree Fahrenheit like that. Then you're going to subtract 32, which is a constant, and multiply this guy by a fraction, which is 5 over 9. And this is going to give you a temperature in degree Celsius. And from the opposite, from degree Celsius to degree Fahrenheit, what are you going to do? You're going to use the opposite of this formula. That means you're going to get your temperature in degree Celsius. Then you're going to multiply this guy by a ratio, which is the opposite of the previous ratio that we used, 9 over 5. Then what are we going to do? We're going to multiply this guy. We're going to add 32 to this guy, not multiply, rather. Going to add 32. In the first case, we are subtracting. And this is converting from degree Celsius to degree Fahrenheit, and from degree Fahrenheit to degree Celsius. Then, if you want to convert from degree Fahrenheit to Kelvin, what are you going to do? You're going to say your temperature in degree Fahrenheit minus 32, like this, multiplied by 5 over 9 plus 273.15. Then from Kelvin to degree Fahrenheit, you're going to say this is your temperature in Kelvin minus 273.15 multiplied by 9 over 5 plus 32. So if you look at the changes from degree Celsius or degree Fahrenheit to Kelvin and Kelvin to degree Fahrenheit, it's the same as first you have to move from the temperature scale of Kelvin to Celsius, then you convert the degree Celsius to the Fahrenheit. Or you're going to start with the Fahrenheit, then you convert it to the degree Celsius, then you are going to convert that guy to Kelvin at the end of the day. That's why the formulas for this end part here, they are looking a bit complicated because they are containing both of these top part formulas. So that is how, in a nutshell, we can convert between different temperature scales. That is, these temperature scales that we've talked about on top here. I've written a lot of arrows, but they're converting from conversions from Kelvin, Celsius, and Fahrenheit. You can interchangeably convert your unit of measurement for temperature between these two guys using these simple formulas that we've talked about here. Some of these, you've already looked at them in secondary school. You already knew them, not some, but all of them. You already knew them in secondary school. We're just trying to repeat the same thing so that at least you have a solid background of this topic, because it is going to get a bit complicated as we move, but yeah, it's not anything to be afraid of. So this is how we can convert from one temperature scale to another. It's also giving us degree Celsius. This one degree Fahrenheit. This one is giving us Kelvin, and this one is also giving us degree Fahrenheit. As simple as that. Those are the temperature scales. Very important, and you're supposed to know these things. Supposed to know these things. Okay, so sometimes, although it's not very common, there's a possibility that you might reach a point whereby there is zero thermal energy in a substance. You don't have any thermal energy in a substance. That means the temperature of that substance is equal to what? Is equal to uh or I can just say it is zero. There's zero Kelvin, zero thermal energy in a substance. That state, we call it as absolute zero. The temperature has reached what we call absolute zero. And that is just trying to tell us that there is no thermal energy. No thermal energy in a substance. And how does a substance which absolute zero is when the temperature, which is the SI unit, we said the SI unit for measuring temperature is Kelvin. When the SI the temperature of a substance is 0 Kelvin, that means it has reached the absolute zero. Or sometimes we can say this is negative 273.15 degrees Celsius. So when a substance reaches negative 273.15 degrees Celsius or 0 Kelvin, we are going to say that substance has reached absolute zero, such that there is no any thermal energy that is remaining in that substance. Hence, no thermal energy, or us calling it absolute zero. The temperature is zero when it comes to Kelvin, and also negative 273.15 in terms of degree Celsius. So that is a brief introduction. We've talked about heat, we've talked about thermal energy, we've talked about what heat is, temperature scales, and also the definition of temperature and how it flows until it reaches thermal equilibrium. Those are very simple things because we're going to apply them. For example, what I said, you're going to get two cups of water. Another cup of water, which was from boiling at 100 degrees Celsius, was to get another cup of water, which was at room temperature at 27 degrees Celsius or so. You mix those two things. Heat is going to flow between the particles of those two systems that you've mixed until it reaches thermal equilibrium, until the temperature is constant. There's no transfer of thermal energy. It reaches some such points, and we're going to calculate those things after we looked at it, or after we look at specific uh, heat capacity and specific latent heat. We're going to use this background to go through to those things. So the next thing that I'm going to talk about here before I run out of time is what I'm calling thermal expansion. Thermal expansion. And what does this mean? Using this statement already, you can tell to say this is expansion that is being related to what? Being related to heat. And what does that mean? That means there is an increase in dimension. Increase in dimension of a substance once subjected to temperature increase. So I'll just use this as temperature increase, which means when when you take any object, then you increase the temperatures are surrounding that object, or you put it on fire, or you supply heat, you supply thermal energy to that substance. It is going to experience an increase. There will be changes in the dimension. So when you are removing temperature, that substance is going to be contracting or constricting, reducing in its dimensions. Whilst if you are increasing the temperature on that substance, it is going to also increase its dimensions. And these dimensions that we are going to talk about are actually three of them. There's what we call increase in one dimension, two dimension, but also three-dimensional increase. And we call this linear expansion. We call this area expansion. Whilst this one, we call it volume expansion. So when expansion is taking place in specific dimensions, we're going to name those types of thermal expansion with different terms. If it's only in one dimension, one dimension rather, like you take a steel rod, just take a rod like that, then you put it on fire or you supply heat to it, then you observe that the length of this guy has changed from this initial length to maybe something um, like that. We are going to call this linear expansion. When you get maybe something which is of two dimensions, there is length here and there is breadth, and both of these sides are increasing in size, such that you, at the end of the day, you see something that looks like this. There's been an increase both in the length and in the breadth. That means we're talking about the area expansion since it's in 2 dimensions. But if it's in 3 dimensions, that means you are doing what? You are uh, expanding the volume of that substance. So this expansion or these expansions are actually going to vary depending on the number of dimensions that you're talking about. And for each of these guys that I've described here, they have specific formulas. The change in the dimension that you are going to talk about, all of these guys have specific formulas. And let me just write the formulas here real quick. So for 1 dimension, which is area or rather linear expansion, we're only experiencing a change in length. So we're going to say this change in length, which is occurring due to a specific coefficient of expansion, is going to be related to or directly related to change in L being equal to alpha multiplied by L0, which is the initial length of that substance, multiplied by the actual change in temperature. So this is giving us what? This is giving us uh, change in temperature, which is T final minus T initial. Whilst this is the initial length that we've been given. What about the alpha that is here? The alpha that is here is just describing to us the coefficient of expansion, of which this is going to be given in units per degree Celsius or per Kelvin, like that, the inverse of Kelvin or degree Celsius. For area expansion, or for area expansion, I'll say change in area will be equal to this guy, gamma, multiplied by initial area, multiplied by the change in temperature, of which this is also what? This is the coefficient of area expansion. For volume, change in volume will be equal to what? Will be equal to beta, of which this beta is just a coefficient of volume expansion multiplied by the initial volume multiplied by the change in temperature, like that. So those are the 3 formulas that we can give. And these coefficients that we've actually given here are related to each other in such a manner that alpha, I'm just trying to show you the relationship between alpha or the 3 coefficients of measurement of expansion. Alpha is equal to 3 times, or not like this. Let me say beta is equal to 3 times alpha, like this. Whilst gamma is equal to 2 times alpha, like this. That means beta can also be equal to what? Can also be equal to 3, this guy, divided by 2. So this is the relationship between the 2 coefficients of measurement, just like that. And when it sometimes you're trying to compare, let's say it's 2 things that are expanding. Maybe you've put gas in a let me say a container. You're going to notice that that gas is going to expand at a faster rate because its molecules are sparsely packed as compared to the surfaces of that container, such that you're going to reach to a point where the gas is going to spill out of the container. And when you want to find the volume that has spilled out of the container, you can just use the formula. Volume of spill is actually equal to the difference in the volume and the coefficients of volume expansion of these 2 guys, of which, since the gas is going to expand at a faster rate, beta of G minus beta of container, like this, multiplied by initial volume, multiplied by change in temperature, just like this. And you're going to find the volume of spill.